First thing, I just want to show this real quick. Not this. Too many tabs. Okay, so if we go up to here, this is what we've gotten so far out of the maze environment. The best appears to be 91, 92%. Couple very odd samples. That should not happen. So that's kind of weird. But the Pareto front currently looks like this. So, I mean, if you just look at this thing, right, you should definitely be able to do better. Like this, there's a little bit of a slope here, it looks like to me. If you just spend a little bit more running time, you should be able to get something better. I think this is probably just a hyperparam optimization failure, and we will be able to get this to be better with better hypers. We're going to look at this real quick just for some insight in case it alters any of what I'm going to do today, because I do have a nice plan for today. We've got learning rate. Gamma, we can actually see based on this that it is bounded too low. We would like to have the max gamma be higher, so I will fix that. Lambda seems to have this nice region right here, around 0.95. That is good. Update epochs, it would like more update epochs, but we this is kind of intentional that we don't let it do more. Yep. And then these don't get swept. Entropy seems like it needs to be allowed to be even lower, which is interesting. Though it's hard to say if it's, sometimes I think that these things just push all the way to one side of the bound or the other. I don't know, maybe this doesn't need entropy. Sweet progress, Pareto front, no mems. Interestingly, yeah, it finds the lower number of M's does better, but that should be much slower. And then batch size, yeah, it's a reasonable one. 4 mini batches. And there you go. Okay, so what we're going to do now, let's get rid of all of this stuff. Don't really need this browser. Really, all I need is this paper and maybe this paper. We are going to start by making a new benchmark. This thing is, we're going to need this machine potentially. Maybe I can run the experiments on a remote box, we'll see. Yeah, I might want to do that. We'll start here. Okay. Neocarbs, perfect. Let me move this as well. So we have a proper stream set up, because I'll be live for a while here. Okay, so right now when we do sweep carbs, we've got puffer carbs here. And then we've got our param space samples here. Whenever I open YouTube, you are live. I stream most of my dev work, and I work decent hours. I didn't stream. I did a couple hours earlier this morning off stream because I needed to focus on the math a little bit. Welcome. I mean, the stream is kind of a, watch reinforcement learning progress happen live and get involved if you're interested. That's the idea. So the goal for today is quality synthetic benchmark for hyperparam sweep algorithms. Make carbs faster, evaluate it on synthetic benchmark, start applying the several mathematical optimizations I've come up with this morning and see if they do better. That is going to be the goal. Yeah, so let me think how I want to do this. Synthetic carbs observation. So what I want to do here is I want to give it 0001s. So let's do 001, which is what we have. Okay. Score. So this is just going to be a variant of the other task that's very, very easy. Your score is just going to be try to get close to learning rate. And then your cost is just going to be, it's just going to be this. And we do need train args, I believe. Okay, so that's our basic task. It is linear. And then we're going to do synthetic percentage task. This one is linear, right? Oh, and this has to also be this. I know how we're going to do this. So this is going to be synthetic basic task, and it's just going to return score and cost. So there's literally no reason to go to higher cost, right? And then synthetic linear task. This is now linear. Cost. You get a log 1. And this is a percentile task. And then let me think what I do. Score times, no. What's a good function for this? Like sigmoid? Yeah, it's gotta be this, right? Turn score divided by over 50. Let's try this. So here we have some basic synthetic tasks. We will see what we do with these. I don't want to log these on. See, I'd like to have these on Neptune, but I don't want to sync them like this. Let's see if Neptune has a way to do this. Init run. Is there a way to just upload a bunch of data? At least until I do carb stuff, I think I can start with this. Test random. Best score. Okay, there you go. Because I'm maxing total time steps on every single run. So of course, then everything is optimal. And there you go. So with a random search, with log sampling, we get the optimal, let's see, learning rate. Something screwy here. Synthetic basic task. Learning rate minus 001. Oh, wait. Okay, so optimal should be 0. There we go. So now we see that random search finds 00103. And then what we can do there we go. So the total cost to obtain these results is right there. I think we're going to want some better plotting utils. This is just crappy random search here. We're just using this to figure out how we want to arrange the plots for everything. See, it's obnoxious because I'd like to just stick this all on Neptune, but I don't want to wait for Neptune to run every trial. Is there like an upload? But we do this. How'd the maze sweep go? On size 32, the current best run is 0.91. Now keep in mind that's not 91% of tasks solved, because the shorter ones, there are more of them because they run faster. but the max score is 1.0. So we would have to run some analysis to see what map size on average it's capable of solving. But sweep goes up. A sweep goes up. I also think we're going to massively improve everything just with better hypers stuff. So we're doing hyperprim algorithm stuff right now. I think I have, well, we're going to see if it works, but I think I have a way better algorithm. Just making some basic synthetic tests right now. Well, neocarbs is just going to be whatever, version of carbs I end up releasing. So yes, I think I'm going to be able to improve over what I have now. Like neocarbs is my algorithm, right? Yes, I've been using this as, fluffy holder. So scores, costs, I don't like this averaging. Yeah, because this isn't the point. Current ideas for improvement? Some math. We will get to it. I have a new function that I think is going to solve the problem of having score functions on completely different scales, some being percentile, some being like, log or linear. It's going to solve all that. I think it's going to solve the problem of not actually filling in points on the Pareto front. It's going to solve the problem of like obsessive filling in of specific regions. I think it's going to solve the problem of not really having a way to consider your compute budget as part of the optimization problem. And it's going to make it a bit simpler as well. Still a very complex algorithm because you still need the Gaussian processes, at least two of them. But I think it makes it simpler. Yep, doing that mostly today. We'll see how much progress I make. I forget if I could get this thing to render through Docker or not. Operation not supported. Lovely. Okay, this thing doesn't run. I hate this shit so much. Like, I just want to use the base plotly. Yeah, we're not doing this. This is stupid. Oh, they just have it hard-coded. That sucks. Um, why does every plotting library just suck? It's my question. I'd like to use plotly, but they did something stupid. So, still doesn't work? Okay, hold on. Maybe I make this work. If it actually... I might be able to make this work. There we go. So I should just be able to keep refreshing this. Cost score. So yep, this is the minimum cost, this is score. I think I want to heat map these by time. Okay, I don't know the API for this. I'm just going to get it to fix this. I swear, every plotting library just sucks. And then it will actually be able to start doing some stuff. Look at how much code this takes. It's like incredibly stupid. This is why I don't ever want to use any of these plotting libraries these days, and I just try to like keep most of it on Neptune or whatever, because all the plotting libraries suck. You think I want to be using a web-based UI? Of course not. It's just all the local ones are even worse. Thought a heck of a lot about that. I think we'll just Verdis. Oh, there. Turbo 256. It looks fine. And I'll tell you what we're doing, why we're doing this in a second. Okay. And show the axis. Well, it goes from blue to red. So you can see that this is just all random, right? This is a random selection of points. And then if we do, we should be able to swap this test out. And then we should get something different. Right, we have to adjust. Right, I have to adjust one thing. The scaling here is off. It's going to make it hard to see. Okay, this is really stupid, but this is not clicking for some reason. I think that just works. See what that gives us. There we go. Let me see. We just have to get this function to be reasonable, and then we'll be able to start showing what this is for. This is essentially, we're trying to get a good test for our hyperparam sweep work. This is too aggressive, this fall off here. No, I don't like this. Exp is too aggressive. Yeah, so this is already like 0 after 0.0. This is like far too aggressive. It's better, right? 2. This is also really dumb because it doesn't take into account the, it's an exponential variable. I literally did this. This is negative. Optimal is -3. That'll be better. Let's try this. Okay, so here's the optimal, this line here, and then you get more points over here. And because the cost for the sampling here, it tries to stick over here, then you get mostly points that are low cost. But yeah, this is pretty nice and dense over here. Okay, this is better. Let's check the basic task, which should be very simple. Yep. You can see you always get, well, it's not dependent on cost. You can get it at whatever cost. So this is just like spread out this way. And then if we do synthetic log task, you can see this front is what starts to get filled in here. Though this log cost is pretty conservative. Let's do try this instead. Just have a higher base. Yeah, there we go. So yeah, that's like a nice log curve right there. And then percentile. Yeah, so percentile, you see it caps out at 1. This one's very close up here. But these are important because you can see that the random search here, it's biased to low time. It's random with normal search ranges. So it doesn't give you coverage uniformly over cost because that's one of the search parameters. That's why it's dense over here. And you're going to see it doesn't give you the Pareto front up here, which is what you want. It does give you surprisingly pretty dense coverage of this portion though. So I want to try carbs on these tasks to basically just see what it does. The one thing that annoys me is that carbs is kind of slow. So ideally, we save results. Actually, why don't we do this? What are carbs? Well, other than bread and pasta and things, carbs is this hyperparameter tuning algorithm from InView AI. that we are currently trying to improve upon. I think we're going to be able to do so quite substantially. I've got some good ideas. I have some very promising tests. But in order to really make sure that this is behaving the way I want some additional synthetic tests to see that in very constrained settings, the algorithm behaves the way that I expect it to in theory. So you're looking for things like uniform coverage or like good coverage of a Pareto frontier. You're looking for, this is a random algorithm, so these points are a bunch of garbage, right? But you are going to want to have like good coverage of this frontier here with the real algorithm. You're going to want it to start off running pretty conservative experiments that don't cost a lot and then run more expensive ones later. You're looking for a lot of properties of these algorithms, and you kind of just want to have confidence that it's behaving sanely. So that's what I'm trying to do at the moment, because I've got some math. I don't know if the math is perfect. We're going to figure that out really quickly. The heck? Okay. That's the current project for my Saturday. Thank you. Yeah, I figure I'm deving. I may as well stream it. I did a couple hours of math work in the morning that was just like think about stuff, look at stuff, throw stuff into Claude that I didn't stream because I kind of needed to focus on it. But I'll share the results of that shortly. Like this stuff I'm doing now is maybe a little harder to get involved in, right? But the vast majority of what I do with Puffer is open source. Half the code is by contributors, many of whom came in with zero RL experience. So, people get to see some of this stuff done live. Maybe people want to jump in and contribute some stuff and help build, it's that kind of a thing. And we're going to be getting a lot more hardware pretty soon for scaling those efforts, which will be fun. I don't know, I pretty much just stream all of my dev. Gotta hit those like 60-hour stream weeks. And let's see if this works. Okay, and then I should have my file here, right? There we go. Perfect. So now we can try carbs on this. Okay, so we're not doing Neptune. It's too damn slow. That's carbs. So this is the problem with carbs, is it's kind of slow because they use ridiculous numbers of samples. So we'll definitely have to look at that as well. I imagine that's got to be the slow part. I can't possibly imagine that fitting a Gaussian process to like 50 points is going to be that slow. What's the general idea behind carbs? You're trying to uncover the Pareto front, which is in this case you take two variables. One is the score that you're getting from your RL task. The other is the cost of that experiment, which is usually the time in seconds it takes to run that experiment. And your goal is to uncover the set of points for which you cannot do both higher score and faster. So it's the set of Pareto optimal points in the sense that you can't do better on both speed and performance. So what you get in practice for this, I can show you a real example of this. Okay, so this is the experiment I have running in this other terminal that's been going for quite a while. So these are the experiments. You can see that this is my version of carbs. It gets better over time. And then the Pareto front is this graph here. So for all the points on this outer curve here, there aren't any points that are up and to the right, which would be higher score, but also faster. So you don't really care about these points over here. These are like bad runs. You want to uncover this frontier. Now, whether carbs does a good job of that or not is a different story. That's why we're working on seeing if we can make it better. But that is the theory of it. Interesting. So my current version of carbs seems to have gotten stuck on the very... It seems to have gotten stuck found the optimal performance at lowest cost very quickly, but now it's not running stuff over here. And why would we want to know that front? Because that gives you the optimal set of, those are the optimal set of hyperparameters in a sense. That tells you for however much compute you want to invest in training a specific RL environment, it tells you what parameters you should use. And you want to know the shape of that front because the shape of that front, okay, the shape of that front could be, it could be this, which means that you have to, like, you want to keep investing compute for quite a while, right? And that this is an environment that scales. It could be like this, which means that you really just care about this point right here and that you don't really do any better by going over here, right? So knowing the shape of this front tells you a lot, but the additional reason for this is that by estimating this front, what you do is you run a lot of very low-cost experiments here in this region that are fast, and then you use the results of these low-cost experiments to predict what hyperparameters are going to be good if you invest more compute. So it actually ends up being a way to reduce your total expense of tuning hyperparameters by a lot. Several-fold. So that's what we're looking at today. Like a good hyperparameter tuning algorithm is a several-fold improvement to just all of RL experimentation across the board. In fact, I would go so far as to say that lack of hyperparameter tuning is the single largest scientific error made in reinforcement learning. Just like across all of research. So this stuff's important. So why does it get stuck here is the question. Oh, it doesn't. I'm stupid. This is the basic test. So here, this is what it looks like by comparison if we do random search. So this is carbs, neocarbs. This is random. Right, synthetic basic, yep. It's a little weird, hang on. Is this really it? There we go. It didn't save. Yeah, so this is your random basic test. You can see that similar to carbs, it does uncover the optimal point here, mostly. It gets lucky once, but carbs like locks right onto it. Next one we're going to do is linear. And then we're gonna start trying to speed it up, I think, after maybe one more. So that we can do this quicker and with more points. Because this is silly waiting for this. Very cool. This so far, this looks quite good, right? I mean, this point out here is kind of questionable. I think this is, well, I actually know because it's blue, this is from the start, so this is from one of the random search points that you initialize carbs with. It's still way far out there. And then basically, yeah, after your initial random points, it pretty darn quickly just gets it. Of course, this is the easiest possible test that you can give. I see output and cost going up, so that's probably a good sign. Oh, and it just massively increases cost. Huh. That's weird. Is it basically gradient descent on score? It's not quite. It's kind of, I guess, sort of. It's kind of a hybrid between that and an evolutionary search around Pareto optimal points. So every point that's on the front is a search locus, it's a search center, and you explore outward from the Pareto points, guided by Gaussian processes that are learned along the way. Okay, here's carbs linear. Holy. Huh. Wait, how did it mess up that badly? Okay, look, it messed up. So these points down here were the initial points, so these are fine, and then it does these, and this is fine. And then it goes up here, which you can see is not optimal. If you draw this line through, this is quite far off optimal. And then it goes all the way over here. So this is too aggressive. And also, like, yeah, this is too big of a jump and too aggressive for being incorrect. And that's probably because of the current, there's some math in the current version of carbs that I have that will cause this behavior. So this is exactly what I wanted the random test to reveal. Next thing will be the logistic, or the log one, I believe. I should get baselines before I start experimenting with stuff. It's worth waiting for the baselines. Got a dip. See you around. Bye. Synth test, test carbs, log test. There we go. Where did that go? Disappeared one. Supplements. Oh, I'm waiting. Could be almost done. Look at this. It still does this this cost 200 nonsense, you see? So I wanted it to be aggressive, but this is too aggressive. 25 experiments and it's already jumping to 200. Right, so you see here, this is too dense, and then this is too sparse. So this, I will forgive it for this, I think. It should probably at least have 1 point here. But I can forgive that. This I can't forgive. This right here, these are recent points. I can tell because they're red. It's a cold hot map. And so these are recent points for which it just messed up its parameter somehow. Which is very hard to do because they're not even correlated. Yeah, so this is not a good result right here. So this is going to give us something to improve on. And yeah, I think that'll be good for baselines for now. So next thing we're going to do is, let me see if we can speed this thing up quite a bit. Config. Num random samples. Num candidates per suggestion per dim right here. Num candidates for suggestion per dim. The hell? Bro. I wasn't this, right? It was this. Okay, what happens if we do this? It's still slow? Now, what is it doing? What is it doing that is that slow? "14 seconds per suggestion." Okay, that's bullshit. So this is all the time right here. That's obscene. You got 12 offs. No. What? What is it doing fitting 12 points? It's fitting a second per point. Screw that. That is so incredibly stupid. Holy. Yeah, so there's literally the only thing slow in here is fitting the stupid model. And I don't know why that's slow. That should not be slow. So get... Something's garbage here. Breaks my term every time as well. Huh? Wait, what? It's training this with Atom? This has a fucking closed form solution. Maybe not with these kernels, it doesn't? Jesus Christ. Five seconds. 5 seconds to train. I wouldn't be surprised if this point it's CUDA overhead. I mean, because how? How do you mess up that badly? Instance is frozen. Okay. This says CPU. So stupid. Yeah, you can see. Literally 5 times slower on GPU. And loads 12 parameters onto GPU for optimization. Stupid. Welcome to the YouTube folks here. So that's ridiculous. That still doesn't make it as fast as I would want. GP Pyro regression. Somebody please explain to me why they have to use Atom. Is it because their kernel doesn't have a closed form solution? Is this a thing? So this whole thing is redundant. This is the first time in a decade that my ML classes come in handy. That I remembered this. Finding the best hyperparameters. The heck? Well, that's dumb. I see. Gaussian processes. At least this speeds it up a fair bit. I don't know why. I don't know why, like, the thing just doesn't quit. Okay, whatever. Let's do this. That's at least 5x faster than it was before. Which is more usable. Okay, so this is percentile. And then this is what it does for percentile. And this is where we see, yep, the other major, okay, this is like beautiful, beautiful data. Because basically every single limitation of carbs that I predicted has come out in the models here. And in fact, is it worth even running this for longer? I don't think so. I think that this just shows it. So here, let's show, first of all, let's do basic. Let me show this off. Because it's very rare in science that you get like a result as clear as this, even with like a toy synthetic task. All right, so here's the random search synthetic task here. This is, where is it? Random search. Okay. So here we go. The heat map, blue points are early, red points are more recent. So it starts off with some random samples, so they're always going to be garbage, no worry about that. But then carbs very quickly finds the optimal parameters here. There's only one optimal set here. There's only one parameter to tune. Cost is not involved at all. So you want the lowest cost version with that one parameter tuned. And you can see it takes a few runs, but very quickly, within a few runs, it gets up to the optimal here of 1, right? And then it hovers around this, but like 0.99, this is good either way. Okay? Now we look at linear, and then we start to see it to fall apart. So here, it's still just one optimal hyperparameter, but you get linearly better with higher cost. So the more experiment time you put in, you double the experiment time, you double your score. It starts to do okay here. These points are sampled a little bit too densely for my liking, but we'll forgive that. Because this is quite a substantial increase in cost. It's, doubling experiment time. So this is not bad. But then it just decides, okay, I know it. boom, I'm going to go all the way to here. And it gets it wrong because it jumps too far. And the reason for this is that the current version of carbs that I have, there's a term in there that rewards you very heavily for absolute increases in performance. There's no normalization on this. So this sees a 4x increase in performance. It does penalize you for variance. So it penalizes you for uncertainty in your estimates, but this is just such a big leap in performance that it does it anyways. And then it does it again, even though it really has no idea what it's doing, because this point should be way, way better. So that kind of shows you it's too conservative and then too aggressive all of a sudden. And that is going to be in the math. That is in the math currently. Like, it is very clear from the formulation that I have why it does this. It's getting rewarded way too heavily for increasing this number. There's no normalization on this number. There's a little bit of attempt to make it a conservative estimate, but that's not enough. Now we go to log. Log looks a bit better, but kind of does the same thing. These 2 points in particular are very recent points, so it kind of gets ahead of itself. It doesn't actually really have a good model yet of the hyperparameter, and it tries to run these expensive experiments and just utterly fails. What we'd like to see is, a smoother filling in of this curve, and then a more gradual extension out to here as it gets more confident. And then finally, this is I think this is my favorite, the percentile test. So this is representing the situation in which you have an RL task where your score is a percentage. So like maybe it's a win rate. So in that case, 0.999 win rate is way better than 0.99, right? But because I'm using absolute improvement in performance here, it doesn't care about that. So it doesn't bother going out here in order to get 0.999 instead of 0.99. It just goes right here. So these are all limitations of the current algorithm. I'm going to be back in 2 minutes. I'm going to get a drink, and then I'm going to explain the new algorithm that I've come up with that I think is going to do way better and solve all of these problems. We're going to test it on all these synthetic tasks, and if it doesn't work, we will debug and attempt to figure out why. Back in 2 minutes. Kill this fly and get a drink. Okay. Does PufferLib have support for planning algorithms like mu0? So PufferLib is not just like, it's not like most other RL libraries where it's a big collection of algorithm implementations. It's mostly lower level tools and infra. So let's put it this way. If you have a implementation of mu0, where you write one, and you use our environment, our vectorization, our tools with that, then it'll run about 100, 1,000 times faster if you were previously bottlenecked by those things. So PufferLib is just lower level tools and utilities. The main implementation that we have is just a PPO implementation. It is very, very fast. It breaks over 1 million steps per second. But yeah, you would have to like port like a CleanRL looking piece of code into our demo script, and then you'd be able to use that. We're not really interested in building out a giant collection of implementations as much as we are figuring out like what is the generally best thing to be doing and then doing that very well. Let me explain the algorithm here. Where is it? My Claude window somewhere. You can just go grab it. Oops. Okay, so this was very long thingy. This formula. So this is percentile of GPY minus percentile y nearest over GPC of x. So what's that mean? In the original formulation of carbs, they've got two terms. They have this acquisition function, this expected improvement term, and then they have p-search. P-search is the easy one. P-search says don't go too far away from hyperparameters that you've currently explored. It doesn't say why or in what circumstance, it just says don't go too far away from stuff you've already done. And then this term here says this measures the improvement as predicted by your Gaussian process that models hyperparameters to score, minus your current prediction of the optimal performance of hyperparameters at any cost of this. So like whatever we think these hyperparameters cost, this function is going to give you the predicted best you can do, the Pareto optimal point there. The problem here, there are a couple things. First of all, this is the difference of two noisy estimators. Second of all, if you assume that these estimators are both perfect, so you have perfect models of these, then this whole thing collapses because everything goes to 0 and you're just randomly sampling points. You're not even sampling good points, you're just randomly sampling points. Also, this gives you no incentive to fill in areas of the Pareto front that you think that you've modeled well. If you have a model and your model says, oh yeah, this region's about this value, and your other model doesn't think that it can improve over that, you're not going to run any experiments there. So you're going to get gaps in the Pareto front, which you don't want. And then also, this here, this expectation, this expected improvement, this biases you towards high uncertainty regions, which then you have to include this term to unbias you. So basically, this whole thing is fighting itself. And then this doesn't even incorporate the cost of the experiments at all. So then this term over here, they do another thing to try to bias towards higher cost regions, which isn't even what you want. You want higher performance regions, even if they are higher cost. So this whole thing is like just a mess that's fighting itself. The idea is good. Explore the Pareto front. That is the good, like that is what you want. But there are a whole bunch of things that are fighting itself here. So the current thing that I have, the current version of what I'm calling neocarbs, has a few improvements, but the key one is I replace this P search term with GPX minus variance of GPX, GPY of X, I mean. So what that says is the absolute performance, take a conservative estimate of the absolute performance of the point that you're looking at. What this does is this biases you towards higher performance regions over time, not necessarily higher cost regions, but usually higher cost regions. There are some issues with this, though, as we just saw. So this does do better than carbs by a lot, but it has some limitations. The key one of which, right here, because I'm using absolute performance, you miss stuff like this percentile, right? Because the absolute performance is not any bigger over here, really, it's just a tiny bit larger. So you miss stuff like this, and then also biasing in the absolute direction like that, again, without taking into account cost, gives you stuff like the other graph that we looked at, where you just try to go too fast and you get it wrong. The new formula here, which I'm hoping should work, is quite different. It's going to replace, we're still keeping the Gaussian processes, at least two of them, but we are going to replace both of these terms. P search, instead, this is going to be divided by GPC of X, which is our prediction of how long the experiment will take to run. And then the first term here is going to look very similar to this, but not quite. We're going to get rid of the expected improvement term, which biases us towards uncertainty. We don't need that. I don't think, at least. We'll see. And we're just going to keep this term, except two things. First, we're going to replace this Gaussian process entirely with just the nearest point on the Pareto front. There are potentially a few issues with that, but we're going to try that. And immediately, if you do that, then you see in the optimal case, you uncover the whole Pareto front, because now GPX, if you have a perfect function, it's just going to go through and make improvements along the whole Pareto front. It's not comparing to a hypothetical of what it thinks that the best points might be. It's actually going to directly improve, directly uncover points on the Pareto front. And then the second thing that we're going to do is apply a percentile transform to these. So we're going to look at what percent of the points is the point that we just discovered better than. And the reason for that is that we want to, well, we're going to have some sort of transform like this, basically, to eliminate the current problem of this happening, where you don't look at these points over here because it's a very small magnitude difference, even if it's better than all the existing points. So that's what we're going to have to do. We're going to start, and we're going to do this incrementally. Hang on. Conservative. Okay, here's your acquisition function. Here we see I currently have EI value times absolute, conservative absolute, times the success probability times max cost masking. These two we will keep. These do not come in. So success probability is only when you have runs failing. That's not a problem for us. The max cost is if you're suggesting experiments that are too expensive, which again shouldn't be too much of a problem for us either. But the initial thing that we need to do so GPY of X is just model dot surrogate output we need to subtract here, hold on. GPY X equals, okay, nearest. Now this one is, I have to figure out how to do this one interactively. So I'm just going to set this like this, and I'll put a breakpoint. I'm going to have to run this to figure out how to do this. It's some weird distance metric. And then we do GP X. Now where's cost model? Surrogate model outputs dot cost estimate. All right, and then we are going to do is there we go. Now all I gotta do is figure out how to do Y nearest real quick, and we will have something to play with. Cool. So I need the current Pareto points, all Pareto observations, what? So then we have costs. So we got costs and scores. And then let me check something. Okay, yeah, argmax isn't going to work for us here. I think how to do this. Well, we need these process estimates up here. Cost estimate. Are these these are torch tensors. We'll just do torch dot tensor. And it's going to be some distant shenanigans here. I don't know why this shit happens. That it like breaks your terminal every time. All right. Tuple has no attribute cost. Pareto, it's not Pareto groups, it's all Pareto observations. There we go. So now, GPYX shape. Okay. And we have Pareto GPYC shape. Yeah. And then we have Pareto costs. One minus one. C. Okay. And then we'll do cost. Yep. GPCX. 1. That's good. That's a cost diff. Good. You want to take ReLU. Take ReLU to cost diff. This is so that you cannot select points that are more expensive than your current one. And then you want to find the minimum, which is just argmin. Okay. Let's see what this does for us. Oh, and we actually don't need the obs, we just need the score. Hey, Spencer. We are currently doing some work on carbs. We got some math going. Messing with Blender. Do I have... Hang on. Let me go find him. Do I have the 3D model on here, or do I have to go find it from somewhere else? Yeah, that's annoying. I might have to go find the old object file. I'm sure I have it. I might have to go find it, though. Let me just look real quick. That would be pretty funny. But don't eat the puffer. Don't touch the puffer. Oh, man. Does it show you your... hell? Well, PNGs. It's not letting me see the, I might have to get it off my PC. There should be the opt file somewhere, though. This is so stupid. They're like censorship or whatever thing is like flagged all the previous messages. It's just like garbage system. Yeah, I have it, but I think it's on a different computer. I have to go grab him. We will get you that model, though. Let me finish my hyperpram stuff. Yep. Is this the case that they're the same cost? That's possible. Yes, that's fine. Okay, let's see this. Let's see what this does. And I shouldn't do percentile, because percentile is the only one of these that doesn't make much sense. For a synthetic linear task. Repeatedly sampling the same point. Okay, let's see why. So this is what carbs linear looks like. Or really our older neocarbs. Oh, Wait, that's way better. What? That's way better. Holy. This is a relatively early point. So I guess this is probably a random sample. Still quite a few down here. But that's like way better. I'm gonna try 50. Take a little longer. I'd like to try 50. Oh, also, hold on. Before I do this, we discovered that this thing doesn't need to be tuned. So there, we'll match now. What are the odds that we just discover the God algorithm? Okay, that's one bad sample. That's pretty good. This spacing here, this is very good right here. This line is very good. Some of these points down here should not be here. I actually wonder if, hold on. I wonder if there's actually a legitimate difference between the number of samples. It wouldn't surprise me. Because when you crank up the number of samples, you get higher variance. We might have to add a conservative term. Well, that's not going to pass. Some dumbass senator just proposed 20 years in prison for downloading DeepSeek weights. It's actually better. I mean, it's like, that's not just a sample difference, right? That's like, oh no, that's way better. Look at all this stuff. I mean, it's got one bad point here, but like, this is not bad either. These points are both Pareto. How do we confirm for certain? Prefer not to have to run it for even longer. Let me think about how this works. What if we make it... Okay, next idea. Subtract the variance, the estimate. Where's our ReLU? Oh, I forgot ReLU. Well, I don't need ReLU here, I only need it there. For Y nearest, I believe. Might make it too conservative, we'll see. So this is a very conservative bound. What we're saying here, right, you're taking the variance off of your estimate. And then you are additionally taking the upper bound, really, like you're adding the variance to the cost. is you're basically saying, assume that you over predicted how well this point is going to perform, and you under predicted the cost, which is reasonable, because as you crank up more samples, this is a sample-based algorithm, so you create candidate points and you score them. The more of those you create, the more whack your points are going to get. And basically, you just get rewarded for having wacky points. So something like this needs to be done. In fact, these might even need some variables on them. But let me just see what this does initially. So our currents are pretty, like this is pretty decent, but this, like as you add more samples, it seems like it gets worse. As you add more samples, it should get better. So here's neocarb's linear. So this is what happens with a bunch of samples. Okay, conservative. Yeah, so this is, yeah, it got to be too conservative, basically. It got to be too conservative because it no longer wants to do, it no longer wants to explore in this region. All right, let's think about that. It's a really huge effect. Didn't even divide by it, I just subtracted the variance. So why does this happen? What about just this one? We should be able to estimate the cost function much more accurately. So variance in the cost should tell you you really don't know what you're doing with this prediction. That might be a good middle ground, we'll see. But I really do think that there needs to be some sort of strategy here. So, I mean, I guess the problem is just that fundamentally with the Gaussian process, right? Um, hmm, it's also not scaled right yet. Hold on. Maybe it just wasn't scaled right. This was our original linear. Conservative cost. Yeah, this is still worse. It's interesting that it is worse. The scale of these things. The heck? I put a breakpoint. Hello? Is it not calling my freaking code? Oh, has it just not been calling my code? Why the hell does it randomly sample? That's insane. Okay, so hold on. Okay, so this is your score prediction. Okay, so this is your variance term. Take square root of it, standard deviation. We have cost. Okay. Target variance. Let's start with this. Okay, we are actually getting data now. See what this does. Now I have one standard deviation instead of squared standard deviation. It's potentially more reasonable. Mm, interesting. A bunch cost 200 points. Maybe not. Conservative score. What in the heck? So you get it over here. How's that happen? Any variation I've tried of conservative in the acquisition function has not worked. Didn't really expect this one though, holy. Is this really the same code? It's very weird. I'll take a second to run. Lol. Yeah, the Twitter midwits with well, GPT is so smart. It's smarter than your junior engineers. You just have everything be a GPT wrapper. It's like funny. Which OS? This is just Ubuntu. And something's weird here because this only went to cost 68 this time. I mean, that is a beautiful curve. But why does it only go to 68? GPY X. It's just the run. Oh, this line. Well, that's funny. All right. Let me run that a second. That's actually going to be a funny ablation. Let me use the restroom real quick. That'll run. I'll be back in a second. I imagine this will be an amusing result. Okay. Let's see what this is. So this is my screwed up experiment where I forgot Y nearest. What? So I'm still wrong. GPYX. How long has this been a thing? Oh shoot, I had that in the whole time. Interesting. Okay, so why would this happen? Let me see. Why would this happen? Okay, this is just an edge case. Yeah, because it's exactly 200. Okay, this is not as bad as it looks. This is just an edge case. Hold on. Let me think about this. Yeah, okay, this doesn't make sense the way I have it is why. I just screwed up the math. Hang on. Yeah, this is how you should mask it. Okay. Yeah, so what was happening is it was computing y nearest as 0 or whatever. And if it computes y nearest as 0, then it's just always going to pick the highest cost point because it's no longer getting evaluated relative to a previous point. It's just getting evaluated in absolute scale, and that breaks it. So basically, there was no baseline. So just a bug, just a math bug. And we will see what it can produce next. Of course, these things are going to take some tweaking. Can't just replace hyperparam sweep algorithms immediately without doing a little work. I'll put another hour in at the moment, and then I'll probably do come back after that. I do have some other work I'd like to get done today, but maybe I push it to tomorrow. We'll see. Okay, better. Significantly better. There should be points in here. And these, I don't know what happened. Well, we also never had the conservative score with fixed. Hold on. Maybe it is this. Not square root. Oops. Maybe it just wasn't working because we didn't have the this set up correctly. Though I think that this will still bias it to be far too conservative. Holy. That does not look like it helped. I don't know why it would do that, though. To be fair, all of these are good numbers, but these should not be scoring high. Subtract the variance. This probably makes it go negative. Yeah, there's probably something screwy with that. Yeah, so if this becomes negative, then you want the biggest possible cost. I think you gotta rally this. Which is annoying. But let's see if that does something dramatically different. To be fair, I don't think I've ever tried that. So maybe every single effort I've had to incorporate a conservative bound has pushed the function to be negative, which then flips your incentive towards high cost instead of away from it. That would make sense. Whereas the problem with making it conservative is you run the risk of just leaving like all the experiments right over here. But let's see if it makes the high cost experiments more accurate. That's the question. Because it is still getting there. Oh yeah, look at that. It's a big jump. So maybe it won't be a problem having this be overly conservative. It even filled in the middle point there. I don't know if this will be sufficient though to resolve the estimate quality. Yeah, so here it only goes up to 100. I mean, the estimate quality is better. It spends way too much time, so it's too conservative. Also, this is kind of too sparse to really tell you on the estimate quality. Okay, let's take the conservative term out now. I wish this thing ran faster. I got it to run at least like 5x faster than the original just by taking it off of CUDA, but I don't know. We shall see. Feed is just gone to garbage. The fact that people are saying GRPO is so good is a little bit concerning because it doesn't look like a particularly like reasonable RL algorithm. It seems like something people should have figured out a long time ago. Oh, 42. Interesting that these are not super recent points. I kind of want to change the way I'm printing out data. And I want to just print out I just want this. And then I also want the come with some music, man. Nah. You may provide your own if you so like. But I don't usually code with music. In fact, I very rarely listen to much music at all. I'm going to write code. I pretty much will only put headphones in for like, I don't know, running PRs or lifting PRs or stuff like that. Maybe this tells us another story. Because that was abysmal. Okay, I don't like this. Here, hold on. Where the heck did I put this thing? Where the heck did I put this? Oh, there its stupid thing is. I don't know why it didn't show up when I looked for time. Try this. Maybe we should also include the predicted. What in the heck? Stupid bots. Go away. Score cost predicted. Let's see. I'm curious to see what this does. I kind of do want it in full precision. I'll just make it wider. I was gonna make it truncate. Oh, obviously the predictions are, yeah, stupid me. So that's not, yeah, that's not gonna work. It's gotta be on observe. Can this work on CSGO? There is some work on that. And yes, generally there is work on RL on first-person shooters. Does it work out of the box or anything? No, it's like a substantial thing to solve. But yes. Thank you. Let me say observation in param. So this is score cost. Just do like this. Okay, so we see the acquisition function going to 0 here, right? These are the random samples. So these first few samples suck. Is the Gaussian process just a bad model? What the heck? It's like the easiest problem ever, and it's got the predictions completely wrong. Did I break something, or has it always been this bad? Well, the cost model is like directionally correct, at least. But it's way off. How do we solve that RL agents learn so slow? That's not a fair comparison. When you're training a new RL model, you're training it tabula rasa. It's a blank slate. Humans have, I mean, we have billions of years. Well, yeah, I guess technically billions of years worth of evolutionary priors built in, depending on where you want to start counting, millions or billions. Um, so of course it's not going to work as quickly. So there are two things for this. One, you do what language models do and you start training on a whole bunch of tasks with one model, though that gets to be more expensive. Not on an industry scale, but like on a smaller research lab scale. Um, or alternatively, what we're doing at the moment is we're starting with the important problems where we can just build fast simulators. If I have a simulator that runs at over 1 million steps per second, I don't care if it takes a bunch of samples because I have unlimited samples. So, and then that lets you do research really, really fast in that area because, you're able to run a lot of experiments. And then, you can discover new methods that will then allow you to solve the harder problems where things are a little slower. All in the plans. Okay, so something is just totally screwy with these models here. Let me see if it happens like this with the, does it happen like this with the original? Let me see, it has to, right? Suggestion in basic. Yeah, because I didn't change the way we're training the Gaussian process at all. Why do models generalize? In RL specifically? Well, because they're trained from scratch on one very narrow task in most work, right? They don't generalize badly when they're trained on a big distribution of stuff. They actually do pretty darn well. I mean, the analog here, right, is that people see a lot of different stuff and solve a lot of different problems. That allows us to solve a lot of different problems that aren't quite like the ones we've seen before. Same thing with RL. Now, yeah, there may be algorithmic improvements and architecture improvements and things here and there, but I think the problem is vastly overstated. Like RL works incredibly well. RL does things that 100 times larger language models that have had 100 times the capital investment still cannot do. That's how I look at it. Hmm. If you change one pixel on breakout, is this if you adversarially change one pixel to make it break? Missed the stream. Well, neocarbs work to begin with, right? What I'm looking at is I'm looking at various modifications to see if I can make it even better, and I'm looking at different synthetic benchmarks. So the success that I had this morning was very, very clearly showing the limitations of the current method on a variety of different tasks. And now I'm seeing if I can figure out how to patch up those holes with different formulations of mostly the acquisition function. Predicted cost is crazy here. So far off. How is it that far off? That could be a data transform issue, to be fair. That could totally be a data transform issue. The model should definitely be better than that. I mean, it's directionally, I can see the cost model is directionally correct. Oh wait, hold on. Is the target estimate different from the surrogate output? I might have just picked the wrong thing for the other one. That looks better, right? 14. And then let me see. Oh yeah. Okay, so it's just, that's fine. Predicted score, target estimate. Let's say this. This should give something at least reasonable within some number of updates. Score. Okay. Yeah, they're directionally correct now. They're just not very accurate. Acquisition function being 0. Why is the acquisition function always 0? Y nearest. Linear relu. And figure out why the acquisition function is always 0. That's insane. Okay, this is 0 here. Yes, this is 0. Hold on, right here. Y is 2. Why is acquisition 0 here? Hold on. I think something's wrong. GPX this is, so this one's fine because the score is predicted lower than Y. Same here, but then this one, the predicted score is higher than Y. So it should be GP YX minus Y nearest. Oh, I'm subtracting in the wrong space. So these scores here, yeah, okay, I found it. So of course it's bad. I'm subtracting in the wrong space. Are we sure? Wait. Observation in basic. Observation in param. Output cost. No, this is the real number input. Where does this get applied? Observation in param. Param space. Obs to basic space obs. Okay, it does look like they actually preserve cost and output here. They transform the space, so I'm not actually in... Hang on, am I in the wrong space or not? Pareto scores. No, I am in the wrong space, because GPX... Yeah. So try this. Target estimate. Cost estimate. You take the difference. Take ReLU, this difference. And then I wonder if the costs are in that space as well. Log cost to cost. Okay, no, it looks to me like log cost to... They transform it back. So here the target estimate surrogate to target, cost estimate is log cost to cost. So they have this. This is good. So now we should be correct. Now let's see if the model is better. It should be. It really should not be that hard to model, especially the cost. So we've got predicted cost and predicted score. Okay? We maintain positive acquisition, which is what we want. These are all very low. To be fair, though, we haven't applied normalization to the top term yet, so the cost bias at the bottom might be too much. Yeah, so this is going to be just a dense, this is just going to be dense at the bottom, right? Wait, did I? Hang on. Neocarb's linear relative. Huh? Did we just do the same test? Oh yeah, no, it's just that the axes are scaled. So look, you get this very nice curve, it's just very conservative is all. Okay. And now if we do this, we do no cost. So this is equally weighting improvements along the front with a linear objective. Okay, it actually, has it gotten the cost estimates? It's closer. No, it still hasn't gotten them. They're better than before, though. Again, they're directionally correct, at least. I'm surprised, though, that it's sticking this close on the front. GPY. Huh. That's what we want. With only one bad point here, the others don't count because they're very early. It's very conservative. Even without the conservative term on it. How is that possible? Why is it just wrong about the hyperparameters? It's a one variable regression. Same thing for cost for that matter. I'm suspicious of one thing that might be kind of dumb. I'm gonna try it though, real quick. Zero, 1 scale. The reason I'm doing this is in case they're not normalizing correctly. Gaussian process, the scale of this data could mess it up. I would hope that they are, but you never know. Doesn't look like this is making a difference so far. Actually, hold on. No, okay. Yeah, definitely not. Huh. It looks to me like the reason that this doesn't work is because the predictions suck. So we almost can't evaluate the core algorithm because the predictions just suck. Yeah, this is going to be this is about the same thing as before. So why is that the case? Fit observations. It's very weird. I'm trying to think if I want to like load up the model. And I almost don't have to though. I know the model sucks. I'm looking at it. Why? I should go get lunch. I'm thinking just like save the Gaussian process and see what the heck is wrong with it. Thing is, the cost prediction should be very accurate. They both should be. It's so easy. And for the score to be that far off is ridiculous. So Samples in basic. Outstanding suggestions. Empty. These are your observations. Do we know the order? Num m's. Total time steps. Is this thing correct? Looks like it. It's really just a question of why this model doesn't fit. Why does this not fit nicely? Real number input. Okay. So here's some data. Hang on. Yeah, I gotta get some lunch. I'm gonna be back. It's It's just a matter at the moment, I think, of the Gaussian processes not fitting for some weird reason. And I got to figure out if that's a problem with the data, or it's a normalization problem, or it's a model problem. There's something bizarre here. But I'll be back in a bit. Gotta get some food, gotta just clear my mind a bit, and then I will be back. So in the meantime, for folks, cool hyperparameter stuff coming soon, as soon as I get all this stuff working. And in the meantime, this is all free and open source at puffer.ai with a ton of cool demos. You can try all of our environments right here in Ocean. Everything from Breakout up to mini MMOs and more. And if you want to support the project for free, just start the repository. Really helps us out a ton. And if you want to get involved with dev, you don't need an RL background, just need to be able to write some good code. You can join the Discord. This is where we organize everything. We have some articles and resources in the blog here. And if you want more, there's some additional content you can't find anywhere else on my X, on the articles, and I post some stuff there as well. So you can feel free to follow that. Thank you, and I'll be back in a bit.